Okay, today we're going to start talking about psychrometrics, which is the last topic of this semester, really. And I want to give some time for us to be able to work on it and be able to do some homework on it, and then have a relief so that you can study for the exam and do all those kind of things so we're equally practiced. I do want to let you know that later on today, on Friday, I'll be releasing the exam 3 grades or some. I'm working through it. I'm trying to figure out how the semester is going to go into the semester, how I'm going to work with grades and how where our standings are and everything like that is. So there'll be another video that's going to be posted in addition to the grades to kind of go over all that. You can watch over the weekend and kind of get yourself prepared for how we're going to approach this at the end of the week, because we'll have 1 week remaining after today of thermodynamics, and it just goes super fast, and it's just like boom, 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 always on you. So that's kind of where we are today. So it's this lecture and then that other video we'll be watching. But let's talk about psychrometrics. Okay, psychrometrics is a special study in ideal gas mixtures, and it's really one of the probably more interesting things that we can talk about in ideal gas mixtures, because you are comfortable or you are familiar with a lot of these ideas, but now we're going to go back to the understanding about why these occur. And these are going to be ideal gas mixtures of dry air and water vapor. So I told you there's going to be a problem about chapter 12 on the final exam. It's going to be ideal gas mixtures. Okay, any ideal gas mixture. Neon, argon, carbon dioxide, all that kind of stuff. Now I'm saying, now we're kind of putting a pin in that, and now we're specifically saying the rest of the mixtures that we're going to talk about for the rest of the semester are going to be mixtures with dry air and water vapor, and we're going to analyze that special mixture for the rest of the semester. Okay, when we call dry air and water vapor, when this comes together, we are going to call this moist air. And what's around you right now, wherever you are, is moist air. You do not have 100% dry air. I don't care where you are, where you're located, which part of the world you're in right now. You're not in any place that does not have some component of water vapor in your air. I mean, if you're only in dry air, let me know. Give me a shout out. Tell me where you are. I'll listen to you. Okay. But again, in this mixture, the dry air acts as an ideal gas, and the water vapor acts as an ideal gas. It's a low partial pressure, so they're both acting as an ideal gas together. And so this is a binary mixture. A binary mixture, 2 things we're going to be adding together there. And we're going to follow the Dalton model. So let's just write here the Dalton model. And it's important that you understand that I'm going to say something like the pressure is equal to the pressure of the air, and I'm going to put air, and I mean dry air. And then I'm going to have PV, which means water vapor. So my subscript for dry air is going to be A, and my subscript for water vapor is going to be V. So this is going to be dry air. And this is going to be water vapor. Okay? And so if we look at this, we know these things apply. Let's just remind ourselves. PV is equal to MRT. Or I can do PV is equal to N R bar T. Or I can do PV is equal to M R bar all over the molecular weight times T. That's the ideal gas law. That's the 3 different ways to write it. We're comfortable with that. And so let's go here and let's figure out what the partial pressure of our dry air is. It's going to be the partial pressure of our dry air is going to be the number of moles of our air times R bar times the temperature all over the volume, or it's going to be the mass of the air times R bar divided by the molecular weight of the air times the temperature all over the volume. And our partial pressure of our water vapor is going to be equal to the number of moles of the vapor times R bar times temperature all over the volume, or it's going to be the mass of the vapor times R bar all over mass of the air, mass of the vapor, sorry, this is molecular weight of the vapor times the temperature all over volume. This is why I don't like doing this myself. Sometimes I get into this way, and you probably heard me a million times say something and write something different, or write something and say something different. I like it when you can call me out, hey Wanklin, what's going on out there? But we don't have that here in this lonely office on Little Kitten Avenue. Okay, so let's understand one other thing, some other words we're going to use. We're going to talk about something called saturation pressure of water vapor. And you know what that is before. We've talked about saturation pressure of water vapor. We're just going to do it in a little bit different way here. So saturation pressure. Okay, saturation pressure is what we looked up in table A1 and A2 and A3. You know, that's what we're looking at there. So let's look at this and let's draw ourselves a TV diagram. And here's our good friend, our vapor dome. And we can go over here and we're going to say this is going to be the partial pressure now of our water vapor. Partial pressure of our water vapor, same as what we were to look at as a pressure of our water vapor before, but now we're specifically saying it's a partial pressure because it's one of two components in a system. Okay, and we may be, let's just say we're over here. This is going to be our, let me draw this a different color here. Let me say this is going to be the temperature of the mixture. Okay, this is the temperature of the mixture. So we're out here, and our water vapor is a vapor. We know that. But if we look back here where we would be crossing this vapor dome, we have another pressure here. This is going to be, we call this P sub G. Okay? P sub G. P sub G is equal to the saturation pressure at the temperature of the mixture. Now, don't confuse yourself. This is nothing different than what we talked about before. If I gave you a temperature and I said, what's the saturation pressure of that? You would go to your charts, your table A2, and you would look at the temperature and you'd find out what the saturation pressure is. It's the same thing we're doing here. The only thing we're saying is now we have a partial pressure of the water vapor. Okay? Now, let's think about that. And try not to make it anything more than it already is. And let me say this: when PV, when the partial pressure of your water vapor is equal to the saturation pressure, we have saturated air. Okay, now here's what I want to. Here's the analogy I'm going to use for the rest of the semester with this stuff. Moist air is a bit like a sponge. Okay, the dry air is the sponge material. Okay, the dry air is kind of a carrier. It's always the same. It never changes. It's just that dry air. Now it may change temperature, of course. It may change, but the amount of it's not going to change. It's like carrying things around. But the water vapor inside that is like the water vapor can change. It's like the water in that sponge. You can add a little bit of water in that sponge and have that sponge, be damp, and you can add some more, and okay, it's going to be a little bit more. But there's a certain point where you're adding so much water to that sponge that it can't hold it anymore, and it starts to drip out. Okay, that's the situation I'm talking about here. When the partial pressure of the water vapor is equal to the saturation pressure, that's when we know that we have as much water in the air that it can hold before it starts to drip out. Okay? There's as much water in that sponge before it can drip out. Okay? Saturation is that tipping point. Okay? And we're going to have to always worry about that tipping point now this semester to see when things are going to happen, because when water starts to drip out, then there's going to be a change that occurs inside of our system we have to work with. So let's try to figure out how we work with this, okay? And that's what we'll figure out in our next video.